mechanics with extensive experience in computational simulations and advanced manufacturing research. Dr. Shikalgar is currently a senior engineer at Tata Consultancy Services, General Motors, Bangalore, where he specializes in advanced welding simulations, Python automatic for resistance spot welding, finite element analysis, and fracture mechanics. His expertise includes Abacus, CAE, FESAFE, and Simufact welding forming, with a strong focus on structural stress analysis and material failure prediction. Prior to this, he served as researcher at Baba Atomic Research Center, Mumbai, where he made significant contributions in fracture toughness evaluation using finite element simulation. His work involved developing computational models for various test specimens and material behavior analysis using GTN material modeling and cohesive element techniques. Dr. Shikalgar has also worked as an assistant professor at Dr. D.Y. Patil College of Engineering, Pune, where he taught courses in solid mechanics, machine design, and finite element methods. Academically, he holds a PhD in fracture mechanics from BAG and ME in Mechanical Engineering from Vishwakarma Institute of Technology, Pune, and BE in Mechanical Engineering from Shivaji University. He is a recipient of the prestigious DGFS PhD Fellowship from the Department of Atomic Energy. Dr. Shikalgar has authored several research papers and book chapters on small punch test techniques, fracture toughness, and computational modeling. His innovative contributions include 4 records of invention in welding simulation. Sir, we are privileged to have him share his knowledge and expertise with us in this FDP. Welcome, sir. And now I will hand over the session to Dr. Shikalgar, sir. Thank you for giving me this opportunity, sir. Hello. Hello, Jubel, sir.
Yes, ma'am,
Are you?
there is one technical issue with the clerk. Please join in 1 minute. Some disconnection there. 1 minute only.
Yes, sir.
Sir, your mic is off, sir. Taslim, sir, your mic is off. Please. Sir, your mic is off. Please check it.
Hello, am I audible?
Yes, sir, now audible, but still your voice is breaking.
Hello?
Please check it. Yes, sir, now audible, sir. But your mic is continuously switching on off, on off. Please check it, sir.
Okay, just
It's not working directly.
no, मेरा advance machine है.
नहीं हो रहा है, मेरा बात मानिए.
Hello? Yes. Okay. Hello, am I audible?
Yes, sir, you're audible. Your presentation is also open. Please share the full screen and please start the session.
Yes, is it visible in full screen?
Yes, sir, now it's visible.
Yes. Thank you for giving me opportunity to give a small lecture on development and application of small punch test. I am Dr. Taslim Shikalgar. I am right now working as a senior engineer in Tata Consultancy Services, and this company is giving services to the other companies like General Motors, Tata Motors, any automotive companies. So I am working as a part of this in General Motors, which is a biggest automotive company in the America. Today I am going to discuss about some fracture mechanics applications and new methodology, which is known as the small punch test, is applicable to get the fracture properties of the any materials. Today's my presentation is I'm going to discuss on basically my 3 papers These three papers are covered during these presentations, and also I added some innovative videos so you can learn how we can utilize this methodology useful to get the mechanical as well as fracture properties. Recently, I published the 3 book chapters. In these books, you can get this information from these books also. This book is available online also. Today's agenda for this presentation, I will give the introduction of the small punch test as well as the fracture mechanics approach. Then I will more elaborate on the experimental program, how we can get the experimental properties with the help of the these specimens. And also I will explain new hybrid methodology to generate the fracture properties using experimental data as well as numerical data. And one of the most important approach is the how to utilize Gerson ductile damage model and ENN approach to get the fracture properties with the help of this PSPT specimens. And after completion of this, I will give the one applications of the PSPT, how we can utilize the PSPT specimens to get the fracture properties at a critical regions. I would like to give the introduction of the SPT. You can see here one animation, left side. And this animation shows about the small punch test, one disc type of specimens having 8 mm diameter or 10 mm diameter, 0.5 mm thickness, which is fixed between two upper and lower dies, and one sponge is coming to deform the specimens. With the help of these deformations, we are getting the one experimental data, that is a load versus displacement data. And with the help of this data, so many researchers are use this data to get the mechanical properties. Here you can see these tensile specimens. This is just having gauge length at 25 mm. I just want to show this one comparison. If we use that much material to get the tensile property as comparatively SPT, so SPT specimens can be manufactured from this type of specimens. Many specimens, more than 100 specimens you can fabricate and you can test and you can generate the parametric study also based on these specimens. And here I took just an image on the internet. This is the CT specimen, which is used to get the fracture properties. And these specimens also needed more materials. So these are the conventional tests, and these conventional tests required large volume of the testing materials. And if you extract these specimens from the working components, then it can impair its integrity. So in these situations, mechanical test techniques based on these specimens are not suitable. So for this purpose, one small specimen techniques are the promising for the characterizing mechanical properties as well as fracture properties. Among these, there are so many methods are available. Among these new innovation techniques is known as the small punch test, abbreviated as a SPT. And this SPT is used to obtain a tensile properties, fracture properties, as well as creep properties. And if you see this, these specimens are needed very small specimens. And major application of this SPT is in the nuclear industry. I will go through it during this my presentation. And now you know that to obtain this type of properties, mechanical property with the help of tensile and CT specimen, there is one standard is available. That standard is provided by ASTM. Now ASTM is also working on this standard, how we can utilize these SPT specimens to get the mechanical property. And now this standard is known as the ASTM standard E3205-20. In 2020, they introduced the first standard regarding the SPT. This I just give the more introduction about the SPT. So I just took 3 images from the literature. If you see this, after the testing of the SPT specimens, you will get this load versus displacement data. And this is not like equivalent to the load displacement data we are getting from the tensile specimen. So how we can get this mechanical properties with the help of these specimens? So many research are generated. One point is here. This is known as the yield load. And second point is here, that is known as the ultimate load. They generated yield stress versus yield load, as well as ultimate tensile stress versus UTS load. These type of correlations are available for many materials. They developed a database for many materials, and based on that database, they generated one correlations. So with the help of this correlation, you can find these mechanical properties with the help of these type of specimens. And if you get any new material, so you need to make a database, because you cannot use old database for the new upcoming materials to get the properties. So that is the another challenge with the help of from this SPT. And here you can see this like these circumferential cracks are observed during the testing. So this is also not useful to get the fracture properties, because no one can predict where crack will initiate and how crack will propagate. So how to find out this fracture properties with the help of specimens, that is also innovative challenging for these specimens. So people know this now with the help of these specimens, how we can find the mechanical properties like yield load by using yield load and ultimate load. So now is the main challenge to how to utilize these type of specimens to get the fracture properties. Advantages and disadvantages like this type of specimens we can use to monitor changes in the material properties of the in-service components. And if you see these specimens, it is easy to perform the experiments as comparatively any standard experiments. And this testing means methodology can be used to study the change in the properties of the irradiated or aged materials. But one of the major disadvantages of this SPT techniques is the absence of the crack in the SPT specimens. So we are unable to get the fracture properties, and no exact relations between SPT parameters as well as actual mechanical properties of the material, like between the yield strength and yield load, and ultimate tensile strength and maximum load. And no direct determination of the fracture properties with the help of these conventional SPT specimens. So unable to determine damage parameters. These are the important to find out the initiation of the fractures or lead to the ductile or brittle fractures. So now upcoming methodology is the pre-cracked small punch test. So here just a few researchers are increased the dimensions of the specimens from 8 mm to the 10 mm into 10 mm, and thickness of the specimen is the 0.5. They introduced a notch or crack. Both are terminologies used in the literature. Sometimes people are calling as a notch, sometimes people are calling as a crack. But for fracture mechanics approach, this is you need to call as a crack. And to generate this type of crack in the specimen, it is very critical part, because you cannot generate natural cracks in the specimens with the help of fatigue loading. So for this purpose, people generated with the help of wire EDM or laser techniques is used to generate this type of cracks. And similar methodology is used to test the specimens. And these are the dimensions. Here you can see these dimensions of the fixtures. And these type of specimens are known as the pre-cracked SPT specimens. This is also denoted in the literature as a PSPT specimens. And with the help of these specimens, you can use any software, commercial software, to get the J integral or CTOD or stress intensity factors at the crack tip. Here, I would like to give this some experimental program information on the PSPT specimens. Here, I've manufactured this type of specimens. You can see these dimensions. I took these dimensions from this CEN code. On the right side, you can see these fabricated one specimens that is having 5 mm into 10 mm into 10 mm thickness and 0.5 mm thickness and 10 mm length and 10 mm width. This geometry I took from the CN code. CN code is the famous in the European countries. They are using this code to make this experimental program for the specimens. So for this approach, you cannot study single crack length specimens. So for that purpose, I fabricated different crack length specimens like this 4 mm, 4.5 mm and 5 mm thickness crack lengths in these specimens. And here I generated one ratio. That is, the ratio is important, like A is the initial crack length and this is the W, width of the specimens. So this number is becoming non-dimensional number, A by W. So sometimes in fracture mechanics applications, people are calling these specimens as a using A by W ratio. So here, if you see this A by ratio is become 0.4, 0.45 and 0.5 mm. And in these specimens, I fabricated crack that is having radius is the 0.1 mm. And this is I achieved a minimum radius in the specimens with the help of wire radium. I tested different crack length specimens. Here I just mentioned this A by W. I tested these 3 A by W ratios crack length specimens. I tested 3 specimens per crack length because I want to see the repeatability. Repeatability is the most important challenge to achieve this. Because if you are not getting repeatability during each test, then these results are quite not useful to get the any correlations in the future. So I just want to test the check the repeatability of the my test results. So I got the repeatability. I observed that my specimen is giving me same behavior in each test. I tested this is for 4 mm crack length, 4.5 mm crack length, and this is a 5 mm crack length. So I'm getting, because these specimen dimensions are very, very small. So I'm from these specimens only able to get this type of experimental data. And maximum you can utilize this type of specimens for the scanning electron microscopy. Beyond this, you cannot get more informations. And if you want more informations like live, so you need to use any camera or any additional methodology to get this information, because these type of specimens are kept in the dye. And so no one can go beyond this and no one can observe how my specimen is deforming during the test. So that is the major disadvantages. Now people are working on this. So they are using one endoscopic camera. So they are just passing this endoscopic camera in this hole, bottom hole, and they are observing how this crack is opening during the testing. That is the upcoming. Next time, right now I am also working on this methodology. I will next time arrange one lecture how we can utilize this, and I will more tell details about this. Now we will discuss about this. I got these 3 type of results from these 3 type of specimens. So I want to utilize this test data during the to get the fracture properties. From this load displacement data, I don't have these correlations to observe, get the fracture properties. So I cannot use directly. For that application, I need to develop first the empirical correlation. So I, based on this data, how I can utilize this test data useful to get the fracture properties. So I decided to use the numerical methodology like finite element analysis. I just generated one similar finite FEA analysis model. And here you can see this. I just meshed the symmetrical model because I cannot use 1/4 model because I am having crack in the specimen. So I am getting only half symmetrical specimen. I just meshed this model, and here you can see this near this crack tip. I meshed using a brick element. Brick element means 8 noded element I used with a full integration approach. Here I did the FE analysis of these specimens with the help of the tensile properties. And then I got the FE results from these specimens only load versus displacement data. Here I just compared my numerical results with the experimental results, and based on these comparisons, I developed additional 2 correlations. One correlations between crack length versus peak load, and second correlations versus CTOD versus peak load. Here I just use the CTOD, that terminology known as the crack tip opening displacement. Initially I used this nomenclature like CTOD, but this is the useful methodology to get the fracture properties from this type of specimens. I will elaborate difference between J integral as well as CTOD, when J integral is useful and when CTOD is useful. So here you can see this image is showing this comparison between numerical results as well as test results. Hello, am I audible? Hello.
Yes, sir. Yes, sir. You're audible.
Yeah, very
Yes, because I am speaking. So here is the comparison. Here you can see this. I can here compare. I am getting numerically peak load here and I am getting experimentally peak load here. So what is the difference between two peak loads? So I want to understand and I want to find out the reasons. Initially, I am unable to find out the reasons why this is happening. So I tested again one specimen. I stopped test at the maximum peak load and I observed this. I observed one my crack is growing at the peak load. So that's why my peak load is not matching with the numerical results. So I observed that significant difference between numerical peak load as well as experimental peak load. And major reason is the some extent of the crack growth observed in the experiments. So here I just similarly got this image at the peak loads. Here you can see this comparison between two images. So anyone can understand this difference is because of this crack growth. So I want to find out the crack growth. How much is crack grown this specimen? So first I want to find out the numerically and then I want to validate with the help of scanning electron ACM techniques. So how we can utilize this picture to get the crack length at this experimental peak load. So for that purpose, we decided to go for additional simulations. So we did some additional simulations for different crack lengths, and these simulations I did to get the load displacement data. I just plotted this load displacement data. You can see this. If my crack length is increasing, my peak load is decreasing. So from this load displacement data, I calculated peak load for each crack length and I just plotted as a crack length versus a peak load data. Here I observed that first correlation, which is the linear, and I generated this correlation, and this correlation is the A is equal to A is the function of the peak load. And this correlation is very important to get. If I put this information like experimental peak load here, if you see this experimental peak load is the always less than this peak load and numerical peak load. If you put this any, like my numerical peak load is 1500, so I am getting this crack length, but my experimental peak load is less. If I go here, so I am getting maximum crack length. So with the help of this correlation, you can find the how much crack grown during the test. Second one is the CTOD, crack tip opening displacement. I want to find out this crack tip opening displacement. This is the methodology available in the literature. Near the crack tip, you need to make right angle triangle. And where this triangle is touching to the crack flanks, so this distance is known as the CTOD. And this is the 2D methodology. I want to use in a 3D. So no any software is able to get this give this data. So for that purpose, I wrote additional post processing code. So I've just provided all node coordinates, and with the help of this tip and all node coordinates, with the help of this data, I calculated CTOD with the help of one additional post processing code. Here just I plotted this CTOD versus punch displacement. And from this, at a peak load, how much is the CTOD? I calculated like this. From this peak load, I am getting this punch displacement data. And for that respective punch displacement, how much is the CTOD? So based on this data, I again generated one correlation that is known as the CTOD versus peak load correlation. And this is my the second correlation. Here I can get peak load data from this experimental data. I need to just put this peak load data in this correlation one. So I will get the crack length, and from correlation 2, I will get the CTOD. So from these correlations, I just calculated crack length with the help of these correlations, and these are the experimental peak loads for this 4 mm, 4.5 mm, and 5 mm specimens. But here I calculated crack growth with the taking respect only 4 mm specimens. So this is my the crack growth observed during the specimens with the help of correlations. And this is the calculated CTOD at the experimental peak load. And here just I plotted these points and I extrapolated these curves. So I got this CTOD initiation as well as whole curve as the CTOD as a function of the crack growth. And this is the fracture properties for these respective materials. So basically these type of curves are available in the literature, but CTOD is the famous in the European country and J integral approach is the famous in the America. So people are maximum using J integral approach. So I converted this data into the J integral, and here I use some test data from the literature for the same similar specimen from the CT with the help of CT specimen. Here just a comparison between the J integral versus crack group data. Here I got this good correlation as comparatively literature data from these PSPT specimens. So this is the one of the important challenge I achieved with the help of these specimens. And this I published this data in this paper, assessment of the fracture resistance data using the PSPT specimens. Second, I would like to go for this Gerson ductile damage model, which is the famous model available in the all commercial softwares for the explicit analysis. And I want to use this Gerson ductile damage model. I'm not going in the formula. Formulas are available in the book as well as the so many literatures are available on this ductile damage model. I want to tell about the artificial neural network approach, how we can utilize this ANN approach to get the ductile damage parameters. So initially, I assumed some ductile Gerson parameters, just randomly 9 parameters, 6 I fixed. I just varied only 3 parameters. I will tell more about it in the next slide, which 3 parameters I varied. I just varied 3 parameters and I performed so many numerical analysis with the help of Gerson parameters. Approximately to perform this type of simulations with the help of damage mechanics model, I think I need approximately 20 to 30 hours for one simulations. I performed almost 100 simulations to get the load displacement data with the help of this type of damage mechanics models. Here I compared all load displacement data with my experimental data I showed initially, and I observed this comparison is important because I observed that I want to make a range of this experimental data. So my experimental data will fall between the upper and lower limit between the FEA load displacement data. So I just observed some data is the below of the experimental data and some data is above experimental data. So based on this data, I just make a one database. Like I observed that my experimental data is following between range. So I based on this database, I prepared one database. I used this database to train the artificial neural networks. I also wrote this code because initially during 6 years before, this type of codes are not available online. Now you can get any type of code online with the help of Python coding, but I used this Fortran coding to generate this type of codes. I wrote this ANN code with the help of my guide, and I trained this ANN with the help of this database, and I use this trained ANN database means this model, and I provided some database, similar database generated from this experimental data, and from this I provided this data and I got this GTN parameters for this experimental database. Here I generated a random database, and with the help of data I numerical. Hello.
Participant, please switch off your mic.
So here I got these GTN parameters for the experimental database, and from this GTN parameter, I again performed some FE analysis. I compared my results with the experimental database, and from this I generated one GR data with the help of this damage mechanics model. Here, these type of 6 parameters I kept constant because this is constant for all metals. This is just a varying if you are going for other than metals, any other materials. So these parameters are constant for the any ductile materials. But 3 parameters are different. That is known as the FN, EFC, and EFF. FN is the void volume fraction at the nucleation. The second one is the void volume fraction as the coalescence, and third one is the void volume fraction as the final failure. So I just varied these numbers and I performed the multiple simulations and I compared this load displacement data with the experimental data. So I observed that my data is falling between upper and lower bound of this numerical data. So how to generate this database to train this artificial neural networks? So I decided to punch displacement. I decided and I finalized the 15 punch displacement values like this from this place, this place, this place. So once you finalize the punch displacement values, you cannot change these punch displacement values. If you change these punch displacement values for the experimental data, then again your wrong predictions. So I just finalized this punch displacement, and for that punch displacement, I calculated each load value for that respective, and I generated for each simulation 15 load data. So here, with the help of 15 load data and these three properties as an output, I use this database to train these artificial neural networks. And after training these artificial neural networks, I similar load data at the same punch displacement to this artificial neural network. Experimental data I provided, and after providing the experimental data to the neural networks, I got this FN, FC, FF as an output. And this is the good way to obtain any damage parameters for any experimental data. So I used this methodology to obtain the damage parameters for this my material. And I have obtained this here. You can see this. I obtained for 3 specimens, 3 different values. So with the help of these values, I took this average of this. This is my average value. This is the net nucleation, coalescence, and I used these 3 damage parameters to perform the numerical simulations of the 5 mm crack length specimens. Here you can see this. Now my simulation is performing exactly like I am getting is the experimental results. That is the biggest achievement for this. I predicted exact numerical results like exact experimental results with the help of these damage mechanics. So my next task is the how we can use this numerical simulations to get the fracture properties. So during these simulations, this is the 4 mm specimen, this is a 4.5 mm specimen, and this is the 5 mm specimens. Here you can see this, my damage mechanics model give me the one blue color, which is the crack growth observed during the simulations. So my next task is how can I calculate this crack growth data at the peak load. So again, I wrote this one small code to get this. I just provided all these numerical node as well as element data to this find out the crack growth, and with the help of this code I calculated the crack growth in the each specimen at a peak load only, and this is the my crack growth observed during the each specimen with the help of these damage mechanics models. I just added this initial crack length. So this is my the final total crack length observed at the peak load. So initially I developed these linear correlations without damage mechanics model. Now I developed a similar correlations with the help of damage mechanics model. So here is the I got this clear idea. I am getting the same results from the damage mechanics model also. Similar correlations. Here you can see this my 2 correlations with the without damage model. First correlation and with second correlation with the Gerson ductile damage model. Second one is the how to calculate the CTOD. Initially I wrote the similar code for the calculate the CTOD from the without damage models. But can I use the similar code for the get the CTOD from these specimens? So I started working on this. Is there any CTOD approach is available for the growing crack? So I studied all papers and I observed that this methodology is not available for the growing crack. I would like to tell you more information. If I shift my crack tip from this location to the new location, if you calculate the crack tip opening displacement at a new crack tip, then you will get the crack tip value, means CTOD value for the next load is the lower value. Not get this type of curve. So this methodology is not available for the growing crack. All researchers are decided to use that. They calculated CTOD at a fixed initial crack. If crack is growing, still they are not changing the crack tip location. So I use this methodology to calculate the CTOD for the growing crack. And here you can see this. I generated CTOD versus punch displacement. I calculated for different crack lengths. And my crack is increasing, my CTOD is increasing. I observed from this type of graphs. So next task is to how we can calculate CTOD versus crack growth data. So here you can see this. This is my numerical simulations. I observed that my crack is started growing, and after few growth, it is. I observed this. My crack is having branching, means crack is going in the two different directions. So I just want to verify, is it possible in the experiment? So I just did one scanning electron ACM image. Here I added this. I just want to see this. Is it possible for? But I observed similar phenomena in the experimentation. That is the biggest challenge for me, because I got similar nature of this crack growth in the experimental also. Next task is to find out the crack growth. So for each CTOD, how much is the crack growing? So I just added one Fortran code in the abacus, so I can get Gauss point coordinates. Gauss point means any element is having 4 to 8 Gauss points. So here I wrote one small code, so my code can give me the each Gauss point coordinates. So I know this initial coordinates and I know the final coordinates. So with the help of each increment, how much is the crack is growing. During the simulations, I calculated with the help of code, and I converted CTOD into the J integral using the conventional correlations. And I just plotted this GR curve. Here you can see this. My blue color curve is, I got this from this type of simulations. And I observed that I'm getting same type of curve, which is I generated without damage mechanics model. That is the one of the challenge for this. And this is the estimated using this Gerson damage mechanics model, and this is predicted from the elastoplastic FE simulations, and this J initiation data is available in the literature. So that is possible because this is the plane strain fracture properties, and this is the plane stress fracture properties, and these fracture properties are always greater than a plane strain fracture properties. So this property is also useful. With the help of minimum materials, you are getting exact property near to the standard properties. So this is data also I published in the literatures. So next, I would like to go for the another correlation. If anyone wants to ask me any question regarding this, now you can ask. I have to more discuss about this, but I would like to give the questions, answers of your questions also. Hello.
Regarding particular this session, if anyone is having question, please ask. Taslim sir, one question that since you registered and that this now test is under the some ASTM some standard, you ASTM has given some standard, correct?
Yes, actually,
And at the starting you told one point that every time when we do the test, we to the material property will get changed. Am I right? Starting time you told us at the starting of lecture you told that once you perform the experiment, the material property will get changed. So we cannot reuse the same test data for next or upcoming test.
Actually, because you needed to perform any test, you need a means you need to handle before this. If newcomer is coming and if newcomer is using similar methodology to test the specimens, so there are chances to get a different load displacement data for each specimens, because new person is going to handle, so some experience is required to perform this type of test. Otherwise you cannot get the repeatability. And second one regarding this, this approach is useful in the nuclear industry. Reason is because nuclear industry is having nuclear reactors. If you see this type of specimens like tensile specimen as well as CT specimens, there is no space is available to the keep type of specimens. You cannot extract these specimens from this nuclear pressure vessel to find out the exact ongoing property. So sometimes so many people are keeping and fabricating these type of specimens, and when they are starting this using this nuclear reactor, they are keeping this type of specimen inside the reactor, and for every year or every 2 years they are taking this type of specimen out and they are testing, so they are finding out these ongoing properties of the nuclear reactor. But if you see this, so many space is required to keep this as type of specimens. But to keep this type of specimens, only less space is required. You can fabricate number of specimens, more in lakhs also. And you can keep this type of specimens in the reactor. And each year you can remove 2, 3 specimens from these specimens. And you can test and you can understand what is the ongoing properties of the reactor. So you can predict the life of the reactor as well as with the help of these specimens. So for this purpose, this technique is very useful. So almost all nuclear industries are using this type of specimens. So recently in 2020, ASTM observed that nuclear industry developed this approach and they are using that approach. So they decided to, we can generate one ASTM standard for this specimen. So anyone can world use that ASTM standard to test this type of specimens. How this type of specimens can be fabricated, how much is the dimensions needed, how much is the dimensions needed for the uh, like upper die, lower die, how much is the dimensions for the punch. So they made this one standard. So each and every person can use the similar fixtures, similar punch, and similar dimensions of specimen to the extract the fracture as well as mechanical properties from this type of specimens. Now ASTM is correlated. This means to do further more research, they are connected with the BRC in the India, and they are taking more data from the BRC, Baba Atomic Research Center, so they can improve the empirical correlations which is available in the standards.
Not normally, what is the material you're testing? 316LN or P91
No,
or
I tested only nuclear pressure vessel materials. There are two materials basically using 2 to 3. One is the T91. Second one is the 20 MN. 20 MN. 1 minute. 20 MN 55, and another one is available 304L. In old pressure vessels, they used 304L, but now they are using T91 and 20 MN 55. This is the these materials they used since last 20 years, and now this
Okay, that is
research is
austenitic, low carbon austenitic steel, 316L, 304L, that category of steel. And
yes,
another P91 means that is a modified nichrome 1 molybdenum.
yes.
That category. Oh, okay. If anyone is having doubt, please ask, or otherwise, sir will continue. Sir, please continue.
Now important task. I told about the J integral as well as CTOD. CTOD is the crack tip opening displacement. Second one is the American approach is the J integral. J integral is the energy release rate is calculated in the ductile material, which is known as the J integral. J integral is divided into two parts. One is the elastic part and second one is the plastic part. Elastic part is known as the stress intensity factor, which is important parameters used in the brittle materials. Stress intensity factor. And J integral is the non-linear energy release rate, which is depend on the path. How much path means are you using to calculate this ahead of the crack tip? That is also important. So this type of correlations between J integral as well as CTOD. These type of correlations are available only for CT and 3-point bending specimens, which is published in the ASTM 1820 standards. But these type of correlations are not available for miniature specimens. So I decided to generate this type of correlations that is known as the M factor. I decided to find out the M factor for this my specimen, PSPT specimens. So how we can utilize numerical methodology approach to find out this type of factor, because this factor is function of the geometry as well as the material property. So we decided to use the multiple properties. I am just showing this one curve. Here we generated this type of curve by varying the yield stress. This is for 300, 400 and 500 MPa. One is the alpha is the Ramberg who is good parameters. Maybe you know that power law equation is the famous K epsilon P raised to N. Similar one equation is available, RO equation, that is known as the Ramberg who is good parameters. There is also one alpha is important and one N is the important. I used this RO equation to generate this type of data, and also I varied the N. N is the hardening exponent. I varied from 5 to 20. So I generated first database input material property, true stress versus true plastic strain data, and I used one data for one simulation. So I generated almost 15 to 20 curves, and I saw these simulations like FE analysis for different A by W ratio. For that purpose, I decided to use only 3 A by W, 0.4, 0.45 and 0.5 mm. So I used a 15 specimen and 15 test this true stress versus true plastic strain data and 3 specimens to total 45 simulations. So I generated with the help of simulations FE results, that is a load displacement data, and also from this FE results I used one code to find out the CTOD. So I got the CTOD from this FE results. But this is the J integral, and to calculate the J integral, all commercial softwares are having J integral approach incorporated all commercial softwares. So easily you can get the J integral approach, which is a path dependent. So I calculated J integral for each specimen ahead of the crack tip, and I just plotted J integral versus CTOD. And I observed that I am getting the linear correlationship between the J integral versus CTOD. And with the help of this correlation, this plot, I generated one M factor correlation, which is the function of the A by W. This is the non-dimensional number, and this is the sigma yield stress divided by sigma UTS. This is also non-dimensional because EM factor is also non-dimensional number. So here I just solved multiple simulations for different EM. I'm just giving one example for this A by W 0.5. If my N is the less, I'm getting the maximum peak load, and if my N is the more, I'm getting the less peak load. And this is just for one yield stress 400 MPa. Similarly, I calculated CTOD versus displacement. Here you can see this, my CTOD is increasing as my A by W ratio is increasing. Similarly, I calculated J integral versus load line displacement from this similar specimen. This I calculated with the help of commercial software. And this is, I observed that my J integral also increasing with the increasing the A by W ratio. So here I just plotted the CTOD versus J integral. Here you can see this J integral versus CTOD. I observed that I am getting the linear correlations between these two properties, fracture properties. So with the help of this, I proposed one correlationship between, that is the M. How I calculated M? Because yeah, I just plotted this J versus CTOD. So M into sigma flow stress is the slope of the curve. And what is the flow stress? Flow stress is the just addition of the yield stress plus UTS divided by 2. And these correlations people are using for the elastic plastic simulations. And if you are using linear simulations, so these simulations, for linear simulations, people are using this correlation. This is the old relationship, and now Kicks and Dogs updated this correlationship based on the flow stress. So I used the second correlations, and based on this, I generated M versus sigma yield stress upon sigma UTS. I observed that I am getting this linear correlations between these two parameters as a function of A by W. So I just proposed that M2 means I just nominated second equation. So that's I'm calling this M2. M2 is the function of A plus B into the this ratio, and I calculated with the help of this correlation. A is the function of the A by W ratio, and B is also function of the A by W ratio. And this type of correlations are available for the standard specimen. I developed these correlations, and I observed that this correlation is useful. I also verified these correlations with the help of this experimental data, and I published these correlations in the Engineering Fracture Mechanics journal. That is my third journal paper regarding the EM factor. So I would like to go for the application of the PSPT specimen. Major application of this PSPT specimen in the nuclear industry to study the change in the properties of the irradiated or aged materials. Second major application of the PSPT to get the mechanical as well as fracture property of the welded specimen. That is the upcoming trends. So people wants to find out the properties of the welded specimens. Suppose they are making two halves and they are welding, and they want to find out the how much the fracture properties they are getting from this weld. So this is the upcoming phenomena. Automotive industry is using this. Third one is the to study the LME cracks. LME means liquid metal embrittlements, cracks generated due to the zinc coating. I will tell more about this also. And to study the nugget properties of the resistance spot welds. These are the four major applications of the PSPT. Second, I would like to show one small video. If you see carefully, this is the BIW body in white. So all joints of the BIW is made by using resistance spot welding. So these dimensions, if you see this, these are the very small spot welding. So people wants to find out what is the ongoing property of the nugget. So here they are connecting two sheets with the help of the resistance spot welding, and they are applying some force and they are passing some current. Now with the help of current they are generating this resistance spot welding, and here you can see this is the weld nugget, and people wants to find out the exact mechanical as well as the fracture property of the nugget. So you cannot use the standard specimen to find out this property. So in this PSPT or SPT is the one of the most challenging approach you can utilize to find out the weld nugget property. Because if you see carefully, this type of nugget diameter are approximately 6 mm length to maximum 8 mm lengths diameters are getting from this type of the weld nuggets. Second important challenge, because automotive industry is using resistance spot welding, but now all automotive industries are using zinc coated steels. Without zinc coated steel, automotive industry cannot use. So zinc coated is applied for the some additional corrosive properties to improve the corrosive properties. But automotive industry observed that some major disadvantages, because during this type of welding, zinc is coated above these two sheets, and because of this current and because of this temperature, zinc is vaporizing, and after this vaporization of zinc, zinc is directly going inside the sheets, and because of the zinc, additional cracks are going to develop. So automotive industry is finding the solution how we can utilize this methodology useful without generating the zinc cracks. Here I would like to show some video which is the most important. This is the two sheets and we are using zinc coated steel. This is the upper electrode and this is the lower electrode. I am just playing one video. Here you can see carefully. Here in this video, you can see the resistance spot welding. Just I am stopping this video at the end. So here you can see carefully. You can observe this zinc is going to inside and generating the cracks here also. Like you can see carefully, here is crack is generated, here is crack generated, here is crack generated, here also crack. You can see here multiple cracks observed during this. So this is the one of the important challenge, how we can find out the crack locations as well as the how much is the crack depth and how much is this crack dangerous, because people wants to test this type of BIW during how much is the during the accident, how much this crack having impact, because safety is the important factor for any automotive manufacturers. So they are thinking that how we can reduce these cracks during this resistance spot welding, because during this manufacturing and during the selling the cars, cracks are not going to do anything, but during the accidents they are playing major roles. So they want safety of the passengers or as well as drivers. So they are thinking how we can utilize and how we can reduce this type of zinc. So all automotive industries right now working on this type of. Here you can see this these type of cracks are generated. These are the dimensions also you can see here. So people are just testing this type of specimens, these welds, and how much is the zinc is the deposited inside the uh, steels. They are finding and they are finding empirical correlations. So how we can predict with the help of numerical as well as damage mechanics models. So how much is the dangerous of this zinc and how we can avoid this liquid metal embrittlement during this resistance spot welding. In this previous video, you can see this so many joints are available and all joints are made of this RSW. And so every joint is having cracks. So you can see this, how many cracks are available in the BIW. That is the important challenge. Not a single crack, so many cracks. So people are still working on this. So here is the one of the challenge. So they can make this RHW nugget, and from this nugget they can generate the one small specimen, and with the help of specimen they can find out the fracture properties as well as the mechanical properties. So I would like to conclude my today's. Uh, So PSPT specimens can be effectively used along with the FE analysis to estimate fracture properties of the structural stress in case of the availability of the limited quantity of the materials. And second one is the new hybrid methodology has been proposed to estimate the GR curves of the structural materials using experimental peak loads and FE analysis. And third is the new methodology has been proposed to predict the GR curves by using FE analysis of the PSPT specimens with the GTM damage mechanics model. And third one is the new empirical correlations is proposed to evaluate the plastic constraint EM factor, which correlates CTOD of the PSPT specimens with the G integral. Now these are the conclusions of the my presentations, but I am available to give the answer to your all questions. Hello.
Now session is open for question and answer
Very
session.
nice session.
You can, if you don't have any questions, you can also discuss with me any challenges regarding this methodology or any fracture mechanics approach or any tensile or CT specimen approach also. I would like to discuss more, because maybe this methodology is new to you. So less people knows about this methodology. Few people knows about this fracture mechanics approach because they studied in a masters. Now they want to introduce this subject in a BTech level also. But slightly this chapter means fracture mechanics is the quite difficult approach to understand, to digest. So no worry about this. I am ready to help you regarding this.
Participant, if you're having any question, you can ask your question, your doubts related to flat element method for fatigue, crack, and other fracture.
If you don't have any question, it's okay. I would like to discuss more about the resistance spot welding, because as a senior engineer, maximum I am working as a resistance spot welding simulations. I'm doing multiple simulations. Now I would like to tell you more. Uh, One company, MSC company, maybe you know that MSC Nastran. That company collaborated with another company that is known as the Hexagon. Now this company is known as the Hexagon. They generally developed one additional software known as the Simufact welding and Simufact forming. I don't know you know or you don't know about these softwares, but these softwares are still in the developing phase. So these softwares are very capable to do this type of simulations like resistance spot welding simulations for a single weld as well as multiple welds. So these softwares are helpful to perform without damage mechanics models. But right now,
Yes, sir. Tomorrow we are having same session by Hexagon on Simu factor by
okay.
Mr. Asim. He will take the session on Simu factor by same company Hexagon.
Okay, but that software is also very useful. They are using this software to do the numerical simulations, this type of, because no one can use any standard software like ANSYS, Abacus, or LS Dyna to perform this type of simulations. And if you want to perform this type of simulations, so you need to write additional subroutines to find out this, to provide the weld schedule, to find out the nugget diameter, how much is the crack length. So SimFact is developed one of the best software as SimFact building, which is the very important. Right now, I don't have because I am giving these presentations from my own laptop, so I don't have that software version. So we are working on that software also. We additionally developed subroutines, additionally developed how to find out the crack lanes, how LM is going to develop during this building, how many cracks are developed, how we can stop these cracks, any methodology. So I'm still working on this. I'm still developing these new concepts. And not for single steel welding. I am developing this concept for aluminum welding also. So how we can utilize laser weldings. I am using like SN curve, master SN curve. People know that SN curve is developed to find out the fatigue properties. So generally SN curves are used to find out the any fatigue life of the any numerical specimens. So suppose you have laser welded specimens. So you cannot develop SN curve from these texture specimens. So sometimes people are using hybrid approach. Hybrid approach means one of the software is available, FE shape developed by Dassault, and one is the EN code that is developed by ANSYS, I think. Both softwares are people are using to find out the structural stress, and based on structural stress they are developing the masterization curve to find out the life of the welded specimens. That is also interesting observations I observed during the industry. I think tomorrow you have sessions regarding the resistance spot welding or semi-fact welding. You can request show some simulations, live simulations. They can show you how they can using these softwares to find out the to predict the zinc coated cracks developed during this type of specimens. I don't know how much depth they are going to tell you, but this is the still now critical challenge. People are hiring a PhD candidates also to perform this type of research. Any question regarding basic fracture mechanics? One I would like to tell you, if you go in the ASTM 1820, so just give me, I would like to share with one. Is it visible, ASTM standard?
Yes, sir. Visible.
This is the ASTM.
Yes, sir.
This is the ASTM 1820 standard. They are using to find out the fracture properties of the any materials. If you go beyond this, they just tells about the more definitions like what is the crack extension, what is the force, what is the crack opening displacement, what is the CTOD, what is the J integral. Here you can see this. They just plotted force versus clip gauge displacements. This is just a load displacement data, but sometimes they are using the crack mouth opening displacement. Here also you can they mentioned how we can calculate the J integral with the help of this EASTM. I'm just going below so I can tell more about the specimens. Here you can see this. They are using this gauge to find out the crack mouth opening displacement. Generally, people are using load versus displacement data, and they are applying displacement here and load here. So they are calculating global load versus displacement data. But in this approach, they are not calculating the displacement of the specimen. They are calculating the displacement of this crack. How much is the crack opening? And they are plotting the crack opening displacement versus the crack mouth opening displacement versus the load. Here they just gave this how much is the how they can utilize this. One major important they are using the chevron notch, chevron notch is the very helpful technique to generate the natural crack. Here, this is the initial crack they developed, and here they performed the fatigue analysis to develop the natural crack. Natural crack is the performing major important role to the get the fracture property. But if you see these PSPT specimens, they are very small. You cannot perform the fatigue analysis to generate the natural crack. If you perform the fatigue analysis, immediately plastic deformation will happen. So you will get the wrong fracture properties from the PSPT specimens. Here, I want. This is the 3-point bending specimens. So these type of specimens also recommended to use to get the fracture properties. They developed some empirical correlations how we can find out the maximum load with the help of function of the yield stress, and S is the distance between this length of the specimens, and B is the thickness and width of the specimens, and from these specimens we are getting the force versus displacement diagram, and from this diagram they are just calculating the J elastic and J plastic approach. And here they are using this J calculation, J elastic. I told that this part is the J elastic and this part is the J plastic. And with the help of this J plastic is the function of the area under curve, this area under curve. And with the help of this J plastic, they are generating the this type of curves like GR curves. I think GR curve is, I think, not available. This type of curve is available. So this is the, they are generating with the help of CT specimen, J versus crack extension curve. And this is the fracture property. So sometimes people don't want these curves also. People want this initiation, J initiation at the zero crack extension. That is also useful property or sometimes. If crack is initiation, so that is the, after that crack is dangerous. So people wants how much is the J initiation. So sometimes of industry using only one value. Is it safe or is it unsafe to recognize these specimens? So people similarly here you can see the CTOD versus crack extension. They generated similar curves, but they used some correlations because ASTM directly not proposing the to calculate the CTOD. They are proposing to perform the J integral approach only. I can tell 1 minute. There is one correlation is available, similar correlation. Here you can see this. I just proposed similar correlation is available, like J, and this is the CTOD, and you can see this. This is the plastic constraint factor, which is the function of the sigma ys divided by sigma uts, and 4 constant A0, A1, A2, A3. This is the polynomial equation is available. So similar way, I developed correlations for PSPT specimens. So now ASTM is also referred my papers, but they are testing this type of correlations for multi materials. They want to, is it valid for all materials? If it is not valid for all materials, so they will find the polynomial constants for the all materials. And I would like to tell one more information. This is just for information purpose. If you go, this is not a new technique, SPT specimens. If you go here, you can see this. This paper is published in 1991. That Mau, X Mau is the published first paper with the help of the small punch test. That is almost 30 years old methodology. And he developed this type of specimens. I think here he developed a first fixture for these specimens. He just tested this type of specimen. He generated load versus central deflection. And with the help of this curve, he just calculated J1C as a function of the equivalent fracture strain. Sometimes it is called as a biaxial fracture strain. So this journey started in 1991. This author published 3 papers regarding this SPT approach. He published a second paper in 1992. Here also, he fabricated this type of fixture, very bold. So he want to measure the dimensions of this type of specimens. So you cannot measure at a single one locations. So he measured at a 5 locations, 1, 2, 3, 4, and he took just average of these 5 locations, and that is your final dimensions of the specimens. So here he tested these multiple specimens, stainless steel 316, and with the help of he found this one non-dimensional number, that is the thickness change, final thickness upon initial thickness, and this is the deflection of the specimens, central deflection divided by T0. This is the useful methodology. Still people are using this non-dimensional number to find out the like properties. That is the still this is non-dimensional number. And this is the 30 years old. Still, if you go and search on the Science Direct, you will get 50,000 papers available on this small punch test. But still people using the same approach developed by Mao. Same this type of equations. Only few beta may be different for different materials. And here also he in one paper, how we can use this approach for the to get the fracture property. He just developed one 1 minute. Here, I just told that he just calculated equivalent fracture strain like ELN, natural log, initial thickness divided by final thickness. And he just plotted as a function of the J integral. And he calculated K and C like linear equation. And with the help of this, he tested so many materials. So with the help of this specimen, easily you can get the J1C. This is old approach, but this is very interesting approach he developed 30 years before. So during my PhD, I started this literature survey. So I observed that these papers are very useful. And I observed that so many less people, only 1 or 2 authors used PSPT approach to find out the mechanical property. So I decided I can use this specimen to find out the fracture property. And I started my research journey. I published only 6 papers and 3 book chapters based on, and still I am working on this fracture mechanics approach.
Sir, regarding the reflection state welding and welding process you showed no slide. Spot welding and the slides you discussed no previously.
No, resistance spot welding.
The spot welding. So any simulation of that one?
No, I don't have simulation because I added only experimental videos. Because I am working for industry, so I cannot share directly this data with you. So I'm just telling that this type of simulations are performed with the help of SimFact forming or SimFact welding tool. And now these tools are very capable to find out the exact location of the liquid embitterment cracks. They developed methodology how we can provide the coating data to the simulations. So with the help of this microstructure, automatically that simulation is showing that location of the ELME cracks. One crack is developed there, one second crack is developed there, third crack, and we actually measured the dimensions of the crack and also compared with the experimental data. So we observed a similar crack length in the experimental data as well as also. But all these work and development is based on subroutines. Without subroutine, you cannot implement these upcoming methodologies. Because commercial softwares already developed solvers, and to change the solvers, they are taking so many times. And now artificial intelligence is coming. So all automotive industry is developing database. So how can use this so many 30, 50 years database to train the artificial intelligence? So we can reduce the time to get the result. Any simulation, if you want to find out the structural results, just to provide these specimen dimensions. With the help of specimen dimensions and material property, you will get the EFE analysis results immediately. These are the results. No need to perform the simulations. So all industries are developing the database to train the artificial intelligence. Or every industry is working on this right now. So they are generating. I would like to give this. If I made one resistance spot welding, by now these type of codes are developed. Is it a good weld or bad weld? Immediately they can tell you with the help of weld schedule, with the help of images. I'm not going in the microstructure, but with the help of seeing the outer view, immediately AI will tell you this is the bad weld. So automotive industry can immediately check this. Really, is it a bad weld or good weld? And they observed AI is 100% predicting correctly. And if this is a bad weld, immediately they are replacing the welds.
And so what about the simulation? Simulation, so how the AI is trying to cover all the simulation area and
I am unable. You are not audible. Can you? Hello.
so how the FEM methods are AI is covering to FEM methods like in the other software. They are trying
Actually,
to control or maybe other thing. No?
actually, there are two methodology. One is the uh, 1 minute. Supervised learning and unsupervised learning. Now industries are using. Industry performed so many simulations before. They still have all data. For example, one of the BIW, they performed so many numerical simulations. So they have so many database. So they are using this database like some zinc coated material, that is the low displacement data. Zinc coated means aluminum, that is the output. Like stainless steel, then that is the output. So they have so many database, and they are using how we can make one good database to train the artificial intelligence. So many artificial intelligence means AI models are available on the internet. If you go in the any chat GPT or Copilot, immediately you will get the any Python code. But by using code, you can make this AI tool. But how you can utilize your previous database to train these AI models, so you can reduce your future simulations time. Now industries are working on this. Because without training, you cannot get output from these AI tools. So how we can train better way to get the exact outputs? So everyone is working on this. Now in all industries, like ExxonMobil, Dassault, ANSYS, everyone is going to develop. Like parametric studies they are developing. One simulations, you can give the multiple parameters. So you will get the multiple outputs. Now ANSYS, Dassault, everyone is using these approaches. Python automation. You can write all 100 parameters one in Excel file, and one Python command will read all these parameters, automatically generate model, automatically generate mesh, automatically. You need to do. Second day you will get the all outputs. Like this is the first specimen. This is the first output. This is the second specimen. This is the second output. Like multiple DOEs, 100 DOEs you can solve with the help of this Python automation.
Participant, if there are any questions, please ask the question. Session is open for question and answer.
Uh, Dr. Zubair is having my email ID as well as phone number. Now, if you don't want to discuss, it's okay. If you want to ask any question, just send me email. Immediately, I will reply you. Regarding the fracture mechanics, regarding my presentations, or any guidance if you want regarding the research work.
Yes, sir. I will share your email ID in the group also. If anyone
Yes.
is asking, please don't ask the question. Sir, but I am not getting one thing, one point. You are saying that finite element method of yesterday also one of the expert from the industry and I asked you the same similar type of question. Dr. Abraham was here. He was AI expert. He is working more than 15 years in the AI field. So similar types of question I asked him. Since he is not familiar with a mechanical background of finite element method and finite element CFD and his so machine part, these parts he was not familiar, but you are expert in this area also. So I say AI, is it possibilities that these kind of area also may be taught because finite element method is simple. It's a so much calculation, mathematical calculation part is already there in the software. And we are giving boundary condition, we are applying the physical physics, everything, all equation in that one. Then we are predicting the result. So AI will take care of this thing also. That is my question.
No, AI will not take care of this. Why I would like to tell you, we are training using some database. Suppose you generated, you applied one boundary conditions and you developed a similar methods for using different materials. So same BC, you developed a different material database like output database, load displacement data, or NEJ integral properties or CTOD properties. Then you are changing the BC. Then again you developed some database. Again you are changing the again one of the BC. So for multiple BCs you are changing and you are solving the multiple simulations. So now you developed this database. And now you are using that database to train the artificial intelligence. So you can use interpolation data only within upper bound and lower bound. You cannot randomly tell that now I am changing the boundary conditions, which is not available in the trained data. You will get the wrong result. Because it will predict based on the extrapolation. And extrapolation may be right or may be wrong. No one can predict. Interpolation is possible. And this is the interpolation approach. Upper bound and limit, lower bound. So you can reduce your time. For example, I am doing tensile test. Similar test I am doing. Na? I am not changing any BC. I am not changing load applied. Nothing. I am changing only material property and dimensions of the specimen. That's it. But to train the AI, you need to perform this, na? Numerical simulations initially. So now automated. Automated means one Excel sheet. You can write 25 gauge length, 24 gauge length, 30, 50, 100, 1000 gauge length. So this is my dimension. This is the like you just write all these information in a Excel sheet and you can tell this is my first simulation parameters. This is my second simulation parameters. First, it will solve simulations. It will generate data and based on this data, you can generate database and you can train. If your specimen is following between these respected dimensions, then you will get immediate output. If you are randomly, suppose I am using 25 gauge length and you give 100 gauge length, you will not get this data from AI. AI give some outputs, but you cannot believe on that results. May be correct or may be wrong.
I request participant, please, if you're having any doubt, please ask the question. Okay.
Actually, I am expecting some basic questions. Why crack is necessary? Without crack cannot. Why can we means why we are not getting fracture properties?
I
I
have
was
so many
expecting.
questions, sir, but as a coordinator, I should not ask so many questions. I have so many questions because it's an interesting field.
But thank you, Dr. Jugar, giving me such a nice opportunity to give a lecture during this faculty development program.
Okay, so no question is there, then I really thank Dr. Tasneem for giving this really interesting session and in-depth knowledge about the finite element method, fatigue, fractures, and some parts of welding also. And I hope so other participants they really they learn a lot of information based in this particular this area. And on the behalf of Aditya University and Mechanical Department Engineering, we thankful to our guest speakers. And now, since its time is over, so now I request the participant to give the feedback for second session, Dr. Rasmu. And now I'm closing the session. Hmm? If you're having any doubt or any questions, you can share on WhatsApp group. I'm sharing the feedback link for second session. Please check it always.
Thank you, sir.
Till the people are joining.
Okay, Dr. Zubair, I am leaving this call.
Thank you, sir. Thank you, sir. Thank you so much, sir.
Okay, okay, thank you.
I shared the feedback link for second session. I request all the participants please respond to this feedback this form feedback link. Closing the session. Thank you all of you. All participants, thank you. We'll meet tomorrow 6 p.m. Thank you.